Hey everybody. So today I'm not in class, but we're going to do lesson 2.8. We'll do a video and then we'll have our homework, and that's what we'll be doing today. So access your own copy of lesson 2.8 notes in OneNote. You might find that at some points you want to pause the video, go fill in some stuff, come back to the video. That would be perfect. So let's make sure we're accessing our own copy in OneNote. So lesson 2.8 starts with a simple table, and we're trying to analyze the table and then decide which of the equations below, those four below, could describe what's going on in the table. So the table shows the relationship between B, the base, and A, the area of some parallelograms. So all the parallelograms have the same height, and so we're just trying to complete the table. So we want to look at this and see, is there a pattern in these first three examples looking kind of left to right, because it's easy to go left to right, where we go from 1 to 3, 2 to 6, and 3 to 9. And hopefully we notice that this is a matter of doing some scaling, because to get from 1 to 3, we can times by 3. To get from 2 to 6, we can times by 3. And to get from 3 to 9, we can also times by 3. So to put this in writing, we take B, times it by 3, and we get A. So let's continue that here. Same pattern, 4.5 times 3 would give us 13.5, and 11 over 2, which is 5.5 times 3, would give us 16.5. As B is getting bigger, A is getting bigger. And then we get to the point where, well, now we have A, but we don't have B. Well, if to get from B to A, we're timesing by 3, timesing by 3, timesing by 3, then we should, just to get back from A to B, is we should just be able to do the opposite, which would mean we're dividing by 3. We're dividing by 3. So 36 divided by 3 gives us 12. 46.5 divided by 3 gives us 15.5. So sometimes we can take A, maybe if we're given A, we can divide by 3 and we get B. So it all depends on which variable you have, which leads us to part 2 here, which says decide whether each equation could be the relationship. So basically we have two relationships here. Just depending on if you have B, then you know we're timesing by 3 to get A, or if you have A, we're dividing by 3 to get B. So let's see if any of our equations describe that. Is there an equation that takes B, times it by 3, and gives us A? Certainly. D, right? Take B, times it by 3, and it equals A. So there we go. And then do we have one where we take A, divide it by 3, and our result is B? Sure enough, option B, we take A, we divide by 3, and we get B as a result. Okay, problem 8.2 says we're going to do some cleanup after a parade. A group of volunteers is helping to pick up trash along a 2-mile stretch of road. The group decides to divide the length evenly. So everybody's going to do the same amount of work. So we need to find the length of a road section for each volunteer based on this many volunteers. Well, we know that we have 2 miles, and we are splitting those 2 miles by a certain number of people. So let's keep it simple. We got 2 miles divided by 8 people. 2 divided by 8 is 1/4, or 0.25. 0.25, or 1/4 of a mile that each person is going to cover. Okay? What if we have 10 people? Same thing. We still only have 2 miles divided by 10 people. So 2 divided by 10 is going to give us 1/5 of a mile, or same thing would be 0.2. Okay, now we should be thinking in our heads like, well, what if we have 25 people? What if we have more people? Well, the amount that we have to cover should get smaller because we still only have, the parade route is 2 miles. So 2 divided by 25 people gives us 0.08 miles that everyone is responsible for. And if we have 36, 2 miles divided by 36 people 2 divided by 36 gives us 0.056 miles. So here, since we know the amount of 2 miles getting split up by different people, part 2 is asking us, can we write an equation that makes it easy to find the length given the number of people? Well, that's what we were doing, right? The length is 2 miles divided by the number of people. The length is 2 miles divided by the number of people. The length, continuing. So what we're doing is we're taking the length that we're cleaning up, lowercase cursive l, is the 2 miles divided by however many people. And in this case, we'll keep it as n because that's for any number of people. So if we want to find by length, then we want to solve, in this case, we want to set the variable equal to length. Okay, number 3 says, find the number of volunteers in the group if these are the amounts that each volunteer is cleaning up. Well, it's the same thing. Is that instead of taking 2 miles and splitting it by the people, we're taking 2 miles and splitting it by the section lengths that people are cleaning. But once again, if you take the 2 miles and you figure out how many of those piece length of sections are in 2 miles, then that tells you then how many people must have been volunteering. So let's take the 2 miles and divide it by a section of 0.4. How many sections of 0.4 are in 2 miles? Well, there's 5 sections, which must mean that there were 5 people because, once again, everybody's doing the same amount of work. So, same idea. What if there's 2/7 miles? Well, we take 2 miles, we divide that into 2/7 sections. So 2 divided by 2/7 is 7 sections, so there must have been 7 people. Same idea. 2 miles divided by 0.125. 2 divided by 0.125. I'm just using a calculator, which means there were 16 sections, so there must be 16 people. And same thing, 2 miles divided by 6/45. It's a little ugly, but whatever, the logic stays the same. Turns out that there's 15 sections, so we must have had 15 people. So part 4 is very similar to part 2. It says write an equation that would make it easy to find the number of volunteers. So we want to find the number of volunteers. But that's what we were doing. To find the number of volunteers, guys, we were taking the 2 miles and cutting it into each of those sections. And if we divided it by the length of the section, it should tell us how many people. So we took 2 miles divided by the length of the sections. So a very similar but slightly different equation. Up in number 2, right, we had the length is 2 miles divided by the number of people. And in number 4, we have the number of people is 2 miles divided by the length of their section. So very, very similar, but depending on what you know, you would use one equation or the other, depending on what you know and what you want to find. Okay, so let's take this idea to the next step. 8.3 talks about filling and emptying tanks of water. Tank A initially contains 124 liters. It's then filled with more water at a constant rate of 9 liters per minute. So let's just think through how many liters of water are in the tank after certain amounts of time. Well, we know that we start with 124 and we are filling, so we are adding the rate of 9 liters times every minute repeated. So 9 the first minute, the second minute, the third minute, the fourth minute. So we know that there's going to be 9 repeated 4 times, so that gives us 36. And we add it up. So in total, there was 160 liters, which would make sense because we were adding the water over time. Part B asks about 80 seconds. Well, wait a minute. We need to make sure our units stay consistent because if we're adding 9 liters per minute, we need to know how many minutes 80 seconds are. Well, convert to minutes, right? 80 seconds divided by 60 seconds. Cut 80 seconds into chunks of 60 seconds. So that's 1.333 repeating. 1.333. Or it's 4/3. Either one you want to use. But either way, there's 124 to start, and we are adding 9 liters per minute, and we're repeating that 1.333 times. So 9 times 1.333 comes really, really close to 12. And remember, or if you used 4/3, it came out exactly to 12. So we didn't quite add as much, but that's because we only went for 80 seconds instead of 4 minutes. So in this case, we have 136 liters. Okay, now what if we don't know how many minutes? What if the hose is just running and we're not really sure? Well, that's okay. We know we started with 124, and we know that we're adding 9 liters per every minute that we're repeating. And look, all we did was just create an expression. 124 plus 9, however many m liters. So when we have a variable, we just end up with an expression. Okay, now number 2 says, how many minutes have passed when tank A contains the following amounts? Well, let's think about it. It has 151, but we started with 124. So let's take 151 and subtract out what was sitting in the tank to begin with, because we just want to know how many minutes have passed, but the minutes only depends on how much water is being added. There was 124 to start, and it was just sitting in there. So if we do 151 minus 124, we get that there were 27 liters that were added. And then if we know the rate is going at 9 per minute, let's cut that by 9 to see how many minutes. Turns out 27 divided by 9, it was running for 3 minutes. Okay, same thing. 191.5 minus what we started with, because that's what was sitting in the tank. So that means over the time, there were 67.5 liters that were added. Again, if they adding at a rate of 9 each minute, we need to cut 67.5 into 9-liter chunks to give us 7.5 minutes. Should make sense, right? There was more water added, which means it ran for longer. Now we just use the example if we're not really sure how many liters there in total. You turn the hose on and you kind of forgot. You forgot to time it, and then it was just running. So how many's in the tank minus what we know is sitting there to start, which this will just stay as an expression. So there was some number of P minus 124 liters added. And then what did we do? Well, we cut that into the rate that it was filling. So we'll do the same thing. So once again, we're just left with an expression. P minus 124 over 9 minutes. And it's kind of strange to leave that as an expression, but we could fill in any letter for any number for P, and it would give us the amount of time. That's what we do, right? We create a general expression that will work for any amount of liters. Okay, tank B is a little different. Tank B initially contained 80 liters and is being drained at a different rate of 2.5 liters per minute. There's a hole and it's draining. So, how many liters of water remain in the tank after the following amounts of time? Okay, so once again, we know that we have 80 liters to start, and we need to figure out, right, how much water drained in 30 seconds. So we need to do our 80 liters of water minus, because it's draining, 2.5 times, but wait a minute, once again, we need consistent units. So we know 30 seconds is 1/2 of a minute, or 0.5. So I'm going to use 0.5. So we know that 80 minus, so 2.5 times 0.5. So 80 minus 1.25, which we know can do our calculator, is there were 78.75 liters. Okay, same thing, right? It's draining. Started with 80 minus 2.5. It was repeating for 7 minutes. That's going to give us 2.5 minus 17.5, which should give us 62.5 liters. If it's draining for each minute, then as more time goes on, we should have less water in the tank, which makes sense. Same idea. What if we don't know how much time? Well, we do know that it starts with 80 and we're subtracting or draining 2.5 liters for every t minutes. So our expression will remain 80 minus 2.5 t liters. Okay, once again, now we want to think in the other direction. Well, what if we know how much water there is? How much time has passed? So we know that they're started with 80, and we're taking away what we know is left to try to figure out how much drained. Well, we know that there were 5 liters that drained. Instead of being added, we know that the difference is 5 liters. And then we're saying, well, if that occurred 2.5 every minute, then we know that it drained for 2 minutes. Same thing. What if we have 32.5? We started with 80. Let's subtract what is currently in there so we can see how much drained. 47.5 liters drained. Once again, if we know the rate 2.5, we can figure out how much time had passed. 19 minutes. That should make sense because a lot more water drained, because instead of 75 liters left, there was all the way down to only 32.5. And then the same idea. Well, what if we don't know how much is in the tank? We forgot to measure it. That's okay. We know that we started with 80 and we'll subtract what's there. We're going to leave this as an expression. So 80 minus V liters were drained. And the same idea. We divided it by its rate every time. Divided by 2.5. So it's going to be 80 minus V divided by 2.5 minutes. Depending on what is left in the tank, we can substitute anything in for V. Okay, so our pattern here was that we knew what was going on. We kind of created an expression in our minds, and then when we were given a variable on the last example, we did have to leave it as an expression. Same thing. But depending on whether you want to know t or you don't have t, or you want to know v or you don't have v, will depend on what type of expression you're going to create. Okay, we're going to leave off the cool down. Let's just go straight to what we should be doing now. So we should be starting our 2.8 homework now, in class, during class time. Even if you're at home, we should be starting it now. This is our assignment. It's posted in Teams. It's also in OneNote. It's due next class, which is Thursday. Remember, no school Wednesday for you guys, so it's Thursday this is due. If you don't finish it now, it's homework as usual. But that we should make sure that that is completed and turned in on Teams for Thursday, and we'll reconvene about what we're doing on Thursday. Okay? Do your best, guys. Appreciate it. Email me with any questions you have, and we'll talk about what's going on. We'll talk Thursday.